All right, everyone. So now we're really going to get into the good stuff. So we've defined work and energy and power, and we've talked about how you might compute potential energy or kinetic energy. Now let's get into really the physical concepts that we will use to solve problems. Conservation of energy is, of course, one of those, and you're probably familiar with the idea of conservation of energy. It says that energy cannot be created or destroyed, but it can be changed from one form to another. That is, all the energy in the world is already out there. But we can make it look different. We can change the way it looks. For instance, I talked about holding my pen up. My pen has potential energy. I'm holding it in a gravitational field. I drop it. That potential energy turns into kinetic energy. Energy stored by being held up in a gravitational field is turned into the energy of motion. Then it crashes to the table, and that energy changes forms again. It probably turns into some thermal energy, turns into some sound waves, which carry away energy. There's many forms of energy. And we can't destroy or create it, but we can shift it around. And so what does that look like? Well, broadly speaking, simply the energy at the beginning should equal the energy at the end. E naught equals E final, or E initial equals E final. But that's an equation that is so simple, it's not practical to use. So in practical terms, what conservation of energy will look like for us is this. We're going to do some accounting. We have to think about what types of energy we have at the beginning, what types of energy we have at the end. And if we add up all of our energy at the beginning, it should equal all of the energy at the end. Specifically, our initial kinetic energy added to our initial potential energy should equal our final kinetic energy plus our final potential energy. And this is where, as I said, I'll try not to mix types of potential energy, because certainly you could add more and more different types of energy to both sides of this equation. But I will try to write problems in such a way that we only have gravitational or elastic potential energy showing up here. That way you only have to keep track of one form of potential energy throughout the problem. And of course, we only have one form of kinetic energy. We're considering the translational kinetic energy, just that energy of moving. All right, so this equation, it's certainly true for the universe as well as closed systems, unless work is done on the system. For instance, friction. So you've got a nice closed system, it conserves its energy. But if something outside that system has some impact on the system, you can change the amount. Now, in the big wide world, in the universe, we still have conservation of energy. But in whatever little box you're trying to define, you can shove some more energy into that box, or you can take some energy out of that box. But to do so, you are doing work on that system. You're changing the amount. And the most common example we'll see is friction. Friction sort of saps the energy out of a system. So the way this would look, if we were to slightly change our conservation of energy equation, we would still do our accounting. We would have initial kinetic energy, initial potential energy, but we might subtract a work term. Remember, we're only going to deal with positive amounts, so we do have to manually put in that minus sign. We wouldn't have to do this with vector calculus, but we're not doing vector calculus. I don't think you guys want to sign up for that just yet. Give it a couple more years. Develop some more mathematical tools. But if we're taking energy out of the system, we have to subtract it out. If we know that there is work done by friction, it's taken away from the system. So we subtract a little bit of energy from what we started with. We started with this amount. We lost some to friction. This is what we're left with. And it could still be in different forms. We could still end a problem with kinetic or potential, or a combination of the two of those. Now, this is going to be the most common situation, where friction sort of saps the energy out of a system. But that's not to say you can't add energy to a system either. In fact, you can. We won't maybe see many examples of this, but you could make corrections to conservation of energy by adding work as well, where you would start with some amount of energy, you get a little boost, and so you're going to end with more than what you started with because you added some. An example of this would be like pushing a child on a swing. A child on a swing, they've got a certain amount of kinetic energy. That kinetic energy turns into potential as they swing up. It then pauses where they're at their highest. They swing back, it turns into kinetic before going into potential energy on the other side. And back and forth and back and forth. Now, if you give that child a shove, if you add more energy, well, then they end up with more speed and they go up to a higher point. You can inject a little bit of energy into that system. And in a situation like that, you would add some work into the system. But if you didn't, theoretically it would stay the same. If there were no friction, a child on a swing or a pendulum would just swing back and forth, reaching the same maximum heights, the same maximum potential energies, and reaching the same maximum speed at the bottom forever. It's only because friction slowly takes energy away that we see this thing slow down. Or if we give it a shove, we can make it go bigger and bigger. So that's conservation of energy, and this is one of the big ways in which we will frame problems. There is another way, however, though, that we will get into in our next video, and that is the work-energy theorem. So come back next time and you'll learn a little bit more about the work-energy theorem. It, along with conservation of energy, form the basis for how we approach solving problems with energy. See you next time.